Hello everyone, welcome to Big Data Thoughts. Today we are going to talk about yet another interesting concept. In Spark, how do we tune the programs that we write? How do we tune memory? Basically, how do we optimize the performance of a Spark application? So let's get started. First of all, let's talk about data serialization to begin with, because this is one of the fundamental things that we need to understand and then see how we can optimize. Because when we are talking about a distributed architecture, there is a lot of data that is moving around between the nodes when the execution happens. So it is important to know what data serialization is. What is data serialization? Simply put, it is the process of converting an object into a stream of bytes so that it can be easily saved, transmitted, read. Now, serialization plays very important role in the performance of any distributed application. So there is no way we can overlook data serialization or not choose the proper type of serialization when we are writing a application that is going to work on a distributed cluster. So this is the fundamental thing that will happen in terms of converting an object into a stream of bytes so that it can get passed on to different nodes or get distributed. Now there are two types of serialization that Spark provides. One is Java serialization, second is cryo serialization. Now default is that Spark will serialize objects using Java's object output stream framework. That's the default, which is the Java serialization. And it can work with any class that we create. That class just has to implement java.io.serializable, and this is something we all know. For any object to be serialized, that the class that we are creating has to implement the interface java.io.serializable. Now we can also control the performance of the serialization by extending the java.io.externalizable. This Java serialization is very flexible. It is by default this is the one that is used, but then it is a bit slow. Why it is a bit slow? Because it creates very large serialized formats for many of the classes. When it converts into a stream of bytes, the objects, the size is bigger, and that is why it becomes slower. So sometimes people want not to use Java serialization because of the impact it has in terms of the overhead of converting the objects into a series of bytes. Now the other alternative that we have is a cryo serialization. We can use a cryo library which is there since Spark 4. This will help us to serialize objects more quickly. It is significantly faster than Java serialization, and it is claimed, or as per documentation, that it is 10x faster. The only limitation that cryo has is it will not support all serializable types, and it will require us to register the classes that will be used in the program in advance. So it does have some cons, but then if we look at speed at which the serialization happens, or the size of the after serialization, the size of the bytes that is produced, that is very compact as compared to the ones created by Java serialization. So we need to cautiously choose what kind of serialization do we want to use. Now the other important thing is memory tuning, because of course when we are writing a Spark application, when we are running it, there are objects or there are operations that are going to be performed in the memory. Now how do we control that or tune that? Three things that we need to remember or pay attention to is: what is the amount of memory that our objects are using, what is the cost of accessing those objects from memory, and what is the overhead of garbage collection. When the object is no longer used, what is the overhead of that garbage collection, because the memory needs to be cleaned up for the other objects to then come back into memory. So these three factors determine how the memory can be tuned. So by default, Java objects are faster to access, but they will consume much more space than the raw data, which means if we are using Java objects, or we are programming in Java, the objects will be faster to access, but they will consume like 5x more space than the raw data which we are storing in the fields. So that needs to be kept in mind. Then memory usage in Spark, how do we look at it? So there was one video I had earlier done on in detail on how Spark memory management works. But if I summarize that, there are two types of memory that Spark operates on, two categories basically. One is execution memory, the other is storage memory. What does it mean? Execution memory is the space or the memory that is used for computations like shuffle, join, sort, aggregation, any kind of operations that we are performing within our Spark application. The memory that is used is the execution memory. So think of it that there is a large block which is the total memory. It is divided into two spaces, execution and storage. Execution part is where all your computations are happening, and storage is the part where you're caching, you're propagating internal data across the cluster. So these are two distinct categories in the storage. So if execution memory storage, there is this whole region or the block of memory is the unified region where you have these two sections, execution and storage. So if there is no execution memory getting used, then storage can use the entire unified region and vice versa, because Spark did not want to restrict saying that okay, 50% is for storage, and storage, if it goes beyond 50%, then the objects will be evicted from the memory. No, if no execution is happening, then the storage can expand and take up all of the memory available, and vice versa. If there is no storage, no caching, no internal data getting propagated, execution can use all of the memory. Okay, but then there is a threshold that is set so that it doesn't happen the storage occupies everything and when it comes to execution there is no memory left. So there is a threshold beyond which it will not expand, but in normal circumstances till the threshold is reached, storage memory can use the entire unified region or the execution memory can use it. Now, two important properties in memory configuration. One is Spark memory fraction. The other is Spark memory storage fraction. So let's understand what these parameters are so that we can tune it perfectly. What is Spark memory fraction? Memory fraction is the size of M as a fraction of the JVM heap space. So what does it mean? If the JVM heap space, we look at it, it is 300, let's say MB. Now the default memory fraction is 0.6, which means the rest of the 40% is reserved for data structure, internal metadata, and safeguarding against the out of memory. Which means that out of the whole of memory that is available to us, there is a reservation of 60% for Spark to internally store its metadata, data structures, etc. Rest of the 40% is available for us to play with. So this particular property sets the value that can be used by Spark internally. Otherwise, we will keep getting out of memory errors. Right? Now the other piece is Spark memory storage fraction. What does it mean? This means that default is 50%, 0.5. Right? This is the space where cached blocks can be kept without being evicted, which means out of the entire memory I am reserving 50% to be my storage memory. We spoke about execution memory and storage memory, right? Now execution, this storage memory or storage fraction is the property which is telling us how much memory can be utilized for storage. Similarly, we also spoke about a threshold. Why we needed a threshold is we didn't want all of the memory to be consumed either by execution or by storage. So that is where this particular property of memory fraction comes in, where you are reserving 60% for Spark internally to operate. So these are the two properties. We can play with this, but keeping in mind the repercussions of setting it too high or too low. Now, how do we, one question which comes to everybody's mind when we talk about memory, execution memory, storage memory, threshold, we understood the concepts, but what is the amount of memory that is actually required for my program? How do I determine that? Now, the best way to determine that is to look at the RDD. What is the amount of memory that my data set will require to create the RDD? So what we will do, or not even create the RDD. Look at it this way: how much memory would I need for the kind of data set that I'm operating on? So the best way to do it is create an RDD, put it into the cache, right? And then look at the storage page. So Spark provides you a web UI to look at different parameters, the storage you are using, how the execution is happening, how many tasks, how many cores are getting used, all of that. So you can look at the storage to see how much of memory is the RDD occupying. That is one way of getting a ballpark of how much your data set would require, right? Now if we want to do this for a particular object, then we can use a size estimator method also. So Spark gives a size estimator that method for experimentation, just to look at, take a ballpark number and then determine how much should I set my variable. How can I actually have memory efficiently utilized by looking at the size of my data set? What should be the threshold that I should be setting? So one of the ways is putting the RDD, looking at the storage in web UI, or using a size estimator function. Okay, since we spoke about data structures briefly, right, that there are data structures that are getting stored in our memory. Now we are tuning the memory, but it is important to tune the data structure also. We cannot have an infinite size of memory to be consumed. So then what are the best practices to keep in mind for the kinds of data structures that we are using? One, we should try to use array of objects and primitive types, okay, instead of using hash maps or Scala collection classes or standard Java or Scala, any kind of collection classes like hash map, hash set and all of that, right? Better to use primitive array of types, primitive array of objects, because they'll consume lesser space. That doesn't mean we cannot use hash maps or collection classes of that kind. We can, but of course we have to know that they will occupy more space. Now the other thing is we should avoid nested structures with lot of small objects and pointers when possible. Of course, if you have nested structures, they are going to take more space. Then we should use numeric IDs instead of enumeration objects, instead of strings for the keys. Numerics are better optimized. If we have less than 32 GB of RAM, then we can set the JVM flag, right, to make the pointers of 4 bytes. So Java will play with pointers internally, right, if you are using Java. Now Spark supports many languages. One of them is widely used is Java. People use Scala, they use Java, they use Python, lot of languages. But if you are using Java, one of the trick is to reduce the pointer size to 4 byte instead of 8. You can do that in the Spark environment file. Now this will help you to reduce the footprint of data. These are some of the guidelines. But it completely depends on what program are you writing, how is your data set. Do you really have to use collection classes, or you can do with primitive? But generally this is the guideline. Then another thing that we can do is, if the objects are still very large, you have optimized the memory, you have fine-tuned your data structures, but still the object is very large, what do you do? Right? The another way to do is serialize them, store them in a serialized form. If we serialize them, they will occupy lesser space, they'll get compacted. How we can do that? We can actually have serialized storage levels set for our RDD. And there are multiple ways to serialize, or multiple types of serialization that an RDD allows. For example, one of them is memory only serialization. We can set the storage level serialization of how do we want to store our RDD. How do we want to serialize it? Because the moment you serialize, it will get compacted. But remember one thing, when you serialize the RDD, the access time or the time to access that RDD becomes slower, because you have to deserialize it every time you need to read it. Every time you are reading the object on the fly, you have to deserialize. So it will reduce your data storage ka footprint, but it will increase the access time. So it's a trade-off. You need to think, what do I need more? Am I okay to have a lag in the access time, but I need my object to occupy less space? That's a conscious call that a developer takes. But it is possible to store the RDD in a serialized form. Okay. Other important thing is garbage collection. Now we all know what is garbage collection. when we are running a program, there are objects that are getting created, stored in the memory. Those need to be evicted for other objects to come in. Now JVM garbage collection can be a problem when we have a large churn, which means there are multiple RDDs that are getting stored, right? These RDDs are stored by our program. Now whenever Java needs to evict the older objects that are no longer used because you want to make room for newer ones, then the garbage collection will run. It will take some amount of time, and there is a cost of garbage collection. The point that we should remember here, that the cost of garbage collection is proportional to the number of objects that are there in the memory. So it is better to use data structures where we are storing fewer objects. For example, an array of int is better than a linked list. So it totally depends on what kind of objects are we storing and how much of garbage collection needs to be done. That there is an associated cost. So ultimately it boils down for us to think about what kind of data structure to use when we are writing a program. Okay, now we spoke about how data structures, serialization, memory tuning, but then apart from these there are few other parameters which can be fine-tuned to make our programs more efficient, like the level of parallelism. So we all know in a distributed application there is parallelism. There are multiple tasks running on a single node also. There are multiple executors which are running in parallel. So Spark, what it will do, it will automatically set the number of map. So Spark will have some map task, right? Now it will automatically set the map task to run on each of the file according to the size and for the distributed reduce operations. So there are two operations, a map operation and a reduce operation. So Spark automatically does that tuning internally to figure out how many maps should run, how many reduce should run. But then when we write a program, we know while in the map phase it can run in parallel, but when it comes to the reduce phase, like operations like group by key, reduce by key, you have to collect the data at one place to run that group by key ultimately. So we have to even think while writing the program, how many such operations are we doing where the data needs to come to one place. The moment you want the data to come to one place, there is a huge amount of shuffle, huge amount of data transfer that is happening in the network. So it is bound to increase the time, it is bound to put a performance hit. So it is better to think of how you are even structuring the logic. Can you avoid these kind of operations where your parallelism cannot be achieved and you have to bring the data to one place? Okay, now the way to set the default parallelism is there is a property in Spark default parallelism. Okay, usually the recommendation is to have only 2 to 3 tasks per CPU core. We all know, and in the Spark architecture video I've spoken about this in detail, that on an executor, depending on the number of cores, we can have those many number of tasks. So usually it is recommended not to have more than 2 to 3 tasks per CPU core, but we can titrate this value as per our need. Data locality. Now this is very important, and as I said, if you write a program which where you see that there is a lot of data shuffle happening across the network, the performance will deteriorate. So what we need to do is the whole Spark works on the principle of data locality, and which means that if the data and the code that is operating on the data are together, then the computation is faster. If the data is spread across, or if the code is separated, the code that needs to execute on the data is separated from where the data is kept, which essentially means data is huge, it is distributed on multiple nodes, etc., then it is going to take more time. So and one more factor is it is easier and faster to have serialized code being sent from one place to another than sending the data, because data is huge. So this principle is what even Spark tries to use. It tries to see what executors can I use or which nodes can I use to have this data locality in place. So it works or schedules the things on the principle of data locality. Also, let us now look at the locality levels. So there four types of locality levels that we can set. The first is a process local, which means that the data exists in the same JVM as the running code. Now this is the best locality possible because this will be the fastest. The data and the code both are process local. The other is node local, which means that the data is on the same node. Now one example can be while we were earlier when Hadoop came in and we were using Hadoop distributed file system, we have seen the concept of data locality in terms of data residing on the same node which is required for that operation. Because the more data we require which is not node local, which is on other nodes, there will be a data movement across the network which will hit the performance levels. So process local is the best. Second, which is little bit slower than process local, is node local, where the data has to travel a bit because it may not be on the same node. So node local is where the ideal situation where the code and the data are on the same node. It is little bit less efficient than process local, but still it is good unless you actually bring in data from multiple nodes. The other is no pref, which means that the data is accessed equally quickly from anywhere and has no locality preference. So we have not set any preference because we know that we can access the data quickly. The last type of locality level is rack local. Rack local means the data is on the same rack of servers, because in a distributed setup there are physical machines also. We may be using virtual machines, but there are actual physical machines which are kept on a rack. So it is rack local means it is on the same rack of the server. So if a data is residing on a node that is on a different rack, that will take more time than a node on a same rack. So it goes in this order, in an ascending order of time. The least time will be taken by process local, then node local, no preference, and then rack local. So this is how the locality levels work, and we can set up the level that we want. So this practically summarizes what are the different things that we should look at when we are talking about Spark tuning. I hope this has given you a brief introduction to go and look at each of them and understand what your program, what can be used for your program to make it more efficient. Thank you everyone. Please like, share and subscribe to the channel to get more interesting videos. Thank you.